This is 1972 IMO problem number 3. Here is a view of this problem. We would like to show that this given fraction is indeed an integer, and the best strategy to show that would arguably be that you would take an arbitrary prime, arbitrary obviously, and for any arbitrary prime, if I can show that the power of that prime in its in the prime factorization of the numerator exceed the power of that same prime in the prime factorization of the denominator, then I would be done. So you have the numerator, the prime factorization of the numerator, check for the power of any arbitrary prime p. That one, the power should exceed that of the power of that same prime at the denominator for the prime factorization of the number at the denominator. There's actually a special notation for that. So this is usually the VP notation. So we basically want the VP of the numerator, which is this 2n factorial, to be greater than or equal to VP of m factorial, n factorial, m plus n factorial. This is just a fancy notation of what I just explained. So next, a couple of observations, obviously, like I usually do. You see all these factorial expressions, and you might wonder how to calculate the power of any given prime when you have a factorial expression. Just as an example, quick example, for instance, if I ask you v sub 2 of 9 factorial, so that would simply mean how many 2's are there in 9 factorial. Well, 9 factorial is simply equal to 9 times that decreasing sequence of numbers, and I want to count how many 2's. Well, in the first round you would identify the even numbers. We have 1, 2, 3, 4 even numbers, so therefore the answer should be at least 4. But then we realize that there are more. Indeed, for the multiples of 4, like 4 and 8, and well, obviously our number stops at 9. For these two, we have at least 2. So we need to add at least 2, because when you have a multiple of 4, instead of 1, you would have 2 multiples of 2's. And finally, we should also check for the powers of for the multiples of 8, because multiples of 8 would have 1 extra power of 2, right? So 1 extra 2 there. And that's the answer. But then when you think about it, so it's possible to express this in this nice way. So that 4 here, which means how many even numbers? Well, all we did check is to calculate 9 over 2 and then to take the floor of that, right? So that's obviously the number of 2's in the numbers less than 9 that are divisible by 2. Plus, how about the number of numbers divisible, less than 9 divisible by 4, and the number of numbers less than or equal to 9 divisible by 8. Does that make sense? In fact, you can actually let this happen forever, and it won't hurt you, right? Why can I do that? Because I know this will be just 0, so it cannot hurt me, right? But it kind of is useful in the sense that it can help us generalize that. So basically, that would tell us that, so therefore v sub p of well, n factorial would simply be equal to, well, n over p plus n over p square, and so on, right? So n over p cubed, and we can, or if you will, we can use the summation symbol for I equals from 1 to infinity. That would be n over p to the ith power. How about that? By the way, I've seen in some textbooks use this instead of this, the EPN notation as well. So this is the special case if you have a factorial, but it's kind of the same thing. I think it's just confusing notation. You can solve this problem without any notation at all. All you do is, as long as you understand this logic that I just did for this example, for instance, that should be sufficient. You can solve the problem without using any of these fancy notations. But going back to our problem now, I guess we're ready. Remember our strategy, right? So if this is to be an integer, the number of p's, or the power of p, in the prime factorization of the numerator should exceed the power of p in the prime factorization of the denominator, right? So that's it. So just check for any arbitrary p, how many, what is the exponent of that p, and then what's the exponent of that p here. All right, so let's do it. Let's start from the numerator. Remember the numerator, so we need the numerator exceed the denominator, right? The power of p. So for the numerator, remember our numerator is equal to 2m factorial times 2n factorial. So therefore, the power of p is for that numerator. For the numerator, well, which is exactly what I just said, VP of 2m factorial times 2n factorial is simply equal to, hey, I can just split these two, right? So it's just VP of 2m factorial plus VP of 2n factorial. What I mean is, just count how many p's there are in the first part, and just count how many p's on the other one, and obviously when you multiply these, the exponents would be added up, right? So like this. But I just found out the formula for that, right, which is just here. So therefore this is simply equal to the summation. So for the first part, I equals from 1 to infinity, it would just be 2m over p to the I, the floor of this, plus, again, summation I equals from 1 to infinity of 2n divided by p to the power I. And we can do the same thing for the denominator. So the power of p in the for the expression in the denominator, which is simply VP of, remember the denominator was m factorial, n factorial, m plus n factorial. That's simply equal to, so I can split them, m factorial plus VP of n factorial plus VP of m plus n, factorial, like that. And like we did earlier, so for the first one, this one is just the summation, I equals from 1 to infinity of m over p to the I plus summation n over p to the I equals from 1 to infinity again. And finally the third one, this one, so n over m plus n, sorry for that, m plus n p to the I equals from 1 to infinity. But then how do I do that? So how do I show that this number for the numerator, so I just picked a random prime p, and for any given random prime, if the power of p for the expression at the numerator exceeds the denominator, then I'm good, right? So but how can I compare these two sums, right? So well, the trick would be well, it's kind of much stronger result than that actually. So what we can do is we can compare together. So I'll just in the following sense, I'll just combine them into the same summation sign. So therefore this is the summation of 2m over pi plus p to the power I should say, p to the power I, and then that's the floor of that, and then the same thing for 2n over p to the I, and close it. And I can do the same thing here. Let me quickly do that. summation. Remember, summation sign can do that. It can do a lot of amazing things, obviously. M over p to the I plus n over p to the I power plus m plus n to the p to the I power. And now what I claim is term by term for all these infinite guys. If term by term, I can, for all I can show that every time each of these terms is greater than each of these terms, and I'm done, right? So show for all I. So show for all I, actually let's be specific, for all I from 1 to infinity, that the expression inside the bracket for the first one, so namely this guy, exceeds this guy. So let's write that down. So 2m, so for all I, show that 2m over p to the I plus 2n over p to the I power exceeds, well, at least, or equal to m over p to the I plus n over p to the I plus m plus n p to the I power. That's it. Okay, so well, yeah, do you see, I can make some simplification here, maybe some substitution. Let me use a different color. Look at that, m over pi here, m over pi, and then another m over pi, and then look at n over pi, n over pi, and then another n over pi. So let's make the following substitution. Let m over pi, let's just call it as r, and n over pi, let's just call it as s. So therefore, the expression that we want to prove is equivalent of proving that 2r plus 2s is greater than or equal to r plus s, s plus r plus s. So if I can show that this holds, then I would be done. But that shouldn't be too hard, because first of all, I claim that I can focus my attention for r and s in the following range, and claim, what's my claim? That's not a claim. Restrict attention to, focus on. So it's enough to focus on this range. Why is that? Because if r or s or both of them are outside this range, yeah, because if instead of considering numbers in this range, you increase, let's say, r or s by 1 or 2, for each increment, you just see that the left-hand side, for instance, instead of 0.2, if you increase r to 1.2, right? So we just decided to increase r by 1 from 0.2 to 1.2. Let's see the implication on for our expression on the left-hand side. So the left-hand side used to be 0.2 times 2, which is 0.4. Now it will be 1.2 times 2, which is 2.4. Does that make sense? So therefore it increased by 2. This one didn't increase. Have a look at this one. The right hand side, this one increased by at least 1, because it's 1.2 now. This one didn't change, and look at that, this one also increased by 1 as well. So therefore the right hand side increased by 2, the left hand side increased by, so it has no effect. And the same thing will happen if you decide to increase s as well. So therefore it's perfectly fine to restrict your restrict attention on restrict to this case. But okay, if r and s are on this range, so why should that hold? I think the game changer is r plus s. I think we have two cases, right? So case 1, what happens, for instance, if r plus s is less than 1? Well, this case is obvious. If r plus s is less than 1, then it would mean that this guy is definitely 0. The floor of this guy is 0, and each of its components are obviously 0, no doubt about that. And indeed, the right-hand side can't do worse than the left-hand side can't do worse than 0, right? Which is the right-hand side is just a big 0. So therefore, this will definitely hold. So no doubt about that. Well, the second case is if r plus s exceeds 1. Obviously, it cannot be more than that. Also because I restricted my attention to this. So therefore, for that particular case, r plus s, the floor of r plus s would be simply equal to 1. The implication would be that, so then it implies that either r or s will be more than 1/2, right? So then either you have two cases. R is greater than or equal to 1/2, or s is greater than or equal to 1/2, or both, right? Or both. And then what happens is that, so these will always be 0, right? So these two won't change because they are restricted to 1, right? So that's this is the upper bound. Versus these two, because at least one of them is greater than 1/2, it would mean that 2 times something greater than or equal to 1/2 would definitely exceed 1, right? So as a result, one of them, say this one, in that case, this would be at least 1. So this would be equal to 1, and God knows, maybe this one is also, right? But for the right hand side, only one of the expressions would be 1, versus the right hand side would definitely increase more than that. And that actually proves that this result, term by term, for every single I, this expression exceeds the other one, and of course, when you sum all these, every single one term here exceeds every single term here. Of course, the sum would exceed the sum of the other one. So which means the power of p in the numerator exceeds the power of p in the denominator for any arbitrary p. So that solves our problem. There's actually a very nice, very cute proof of solving the same problem, building a recursion, which is really almost a magical solution. Let me share that with you, and then let's call it a day. So consider this expression. Let's call it fmn. I claim, so this is a bold claim here. I claim that f of mn is simply equal to, okay, so this one is the following. Okay, so I will ask you to verify that. So 4 times f of m n minus 1 minus f of m plus 1 n minus 1. Okay, so I claim that this expression holds for all mn, right? So you can easily verify that. Let me quickly verify this. So verification, or proof if you will. Let's say proof. This is a very nice recursion, isn't it? But let's quickly prove it. Let's start from the right hand side and see if we can get to the left hand side. So we have 4 times. So I will replace n with n minus 1, right? So our expression will become 4 times 2m factorial. The first one didn't change. The other one would change. It would become 2 times n minus 1, which is 2n minus 2 factorial, and all divided by m factorial times n minus 1 factorial, and then times their sum, m plus n minus 1 factorial. So that's the first part. The second part is just minus, it would be just, well, 2 times m plus 1, which is 2m plus 2 factorial, divided by 2 times the second guy, 2n minus 2 factorial, all divided by the first guy, m plus 1 factorial, the second guy, n minus 1 factorial, yes, and then the sum of the two, which is m plus n factorial. Okay, so we started with the right hand side. Let's see if we can get to that one. Okay, so remember that I'm trying to liken this expression to this one. So therefore, let's try to get the same denominator, m factorial, n factorial, m plus n factorial. So I already have an m factorial here. in order to make it n factorial here, I will need to multiply both the numerator and the denominator by n. Let's do it. So 4 times n times, so I multiplied it by n. I have 2m factorial. And then for the second one, I'm missing an m plus n, right? So therefore, I still keep this one, 2n minus 2 factorial, and then I'm adding an m plus n as well. So, and then this way I can add both to the denominator the same thing, which is m factorial times, I added an n here, so therefore this one became n factorial, and I added an m plus n, so therefore this one became m plus n factorial. Minus, okay, we do the same thing on the right hand side. Hey, on the right hand side I have some extra stuff. I will definitely add an n here, both to the numerator and I don't have to do anything. The only thing is I have an extra m plus 1 here. Luckily it will cancel with that one, so therefore I will factor out 2m plus 2. It will cancel with the m plus 1, so there will be a 2 remaining there. I will still have an 2m plus 1 left here, 2m plus 1, still this one remaining, 2m plus 1 factorial, sorry for that. Oh boy, I keep making these silly mistakes. 2n minus 2 factorial, and remember I said that I need to add another n here, so that so I have m, just m now, m factorial, I have now n factorial and m plus n factorial. How beautiful is that? So my denominator now matches with the denominator of the original expression that I want. So all I need is to show that the numerator is indeed 2m factorial times 2n factorial. So let's keep working on that. So I no longer need to worry about my denominator, so let's just write it up front, n factorial m plus n factorial. Okay, so let's be careful on this one. So I have a 2m factorial here. I have a little bit extra here, so therefore I can factor out the 2m factorial. Let me go ahead and do that. So 2m factorial, I factored it out. And then I realize I can factor out n as well. Do you guys see that? I can factor out an n. Let's do that as well. And that's it for now, I guess. Okay, so let's see. Let's go slow. Okay, so I have a 4 left here. I already factored these two, so I have 2n minus 2 factorial, and then I still have an m plus n here, minus, I already factored 2m factorial, so there's still a 2m plus 1 remaining here, so 2 times 2m plus 1, and then the 2n minus, oh, I should have seen that earlier. I should have taken that out as well. Ah, shoot. Okay, and that n is already taken out. Alright, so let me go ahead and take out the 2n factorials again. So therefore I can just delete them and I can just put it here right away. Okay, so what is remaining inside? I have, well, I have 4m here. I have minus 4m, so these two would cancel out. That's perfect. And then I have 4n minus 2. Okay, 4n minus 2. Okay, that's what is left. 4n minus 2 is just 2 times 2n minus 1. Oh, that does the trick. Okay, perfect. Okay, so therefore what's left is my denominator is already fixed. And look at my numerator. I have 2m factorial. That's just beautiful. And then look at that. I have 2n minus 2 factorial times 2n minus 1. So therefore it was 2n minus 1 factorial. And then I further have a 2n. So that's just 2n factorial. Whew, so therefore the claim is true. So, but what is the benefit of this claim? Well, if this claim is true, I think I can do an inductive step to do this. So all I will need is, if I can, using this recursion, let's see if it works for n is equal to 0. So for n equal to 0, f of m0 is just equal to, well, you just plug it in, right? So it will just give you 2m divide 2m. Okay, it's just 2m factorial divided to m factorial divided by m factorial times m factorial. Hey, this is just 2m choose m, right? And indeed this is an integer. So therefore the base case looks like it works. Yeah, so it works for all n, right? So the base case works for all n, right? So so the base case n is equal to so this works for all n. Now we can do our inductive step. We assume that it works for f of m comma n minus 1 for all m. So let's do it in this space here. So let's bring it over here. So assume it works. Or when I say it, I mean f of m n minus 1 is an integer for all choices of m. Then all I do is, if I can show that, so if using this, let's assume this is true for all m, then show f of m n is also an integer, right? But this is obvious, right? Because if you know that this one is an integer for all m, then look at what it is. It's the same thing, n minus 1, n minus 1 here. It means that regardless of the m here, this is an integer. So this is an integer, and boom, this one is also an integer. Integer minus integer, you get an integer. And claim proven, right? Show it's almost immediate, right? I mean, for most people, it's very difficult to see this expression. So that's why our first method, which is kind of, I think it was okay, right? I don't think it was any difficult at all. That solves this problem. It kind of reminds me also the USAMO 2016 USAMO problem, I believe number 2. In a sense, obviously the 2016 USAMO problem is significantly harder than this one, but it's kind of the same logic. The way to attempt the problem is the same logic. But hope you will enjoy this video, and looking forward to see you guys in our next lecture.